Log on, tune in, find out. Another good idea from Cambridge.
And he's going to talk on optimal expansion methods from medical imaging.
Thank you. Good. Thank you very much. Thank you for this kind invitation. I enjoyed very much the atmosphere. Actually, I enjoyed also the bars. But if I have advice, don't make it before your talk. So anyway, so I'm going to explain what we have been doing on this expansion methods. Actually, as you know, in order to solve the inversion imaging problems with satisfactory resolution and stability, we have to add the structural information or supply missing information. So this is the whole idea. And one method of doing this is expansion methods. You can see it like a regularization. And this expansion methods are used for two things: for scale separation and for reconstruction of internal energy in multi-physics imaging from small internal changes in the medium. For scale separation, in many problems you want to image small targets, so you have a small parameter there, and you can take advantage of the presence of those small parameter in order to understand what kind of information is in the signal, in the data, and then design inversion and or optimal design methodology to make the inversion with good resolution and with good stability. And actually what we have been doing is first using this expansion methods to understand the information contained in the data, then build inversion and optimal design methodology, and then investigate their robustness with respect to incomplete data, measurement and medium noises. And what we would like to have is to have the best imaging function for a specific problem. And the best is in the sense of resolution and stability. That's the idea. So let's take a small size targets. There is small size targets. They could be potential tumors at early stage, and we want to image these targets. Actually, if you think about your measurements, you have two kinds of measurements. Either you have boundary and scattering measurements. This is kind of far field measurements. And then whatever you are doing, the only thing that you can do is anomaly detection. You will detect and you reconstruct features of the inclusion. But if you have internal measurements, it's much richer information. Then you can think about the distribution of physical parameters. You may get distribution of physical parameters. The way to do it is should be non-iterative. The way to make anomaly detection could be the way to make distribution of physical parameters should be iterative, and the way to make anomaly detection could be non-iterative, could be kind of direct imaging. And when you have boundary measurements but from internal perturbation of the medium, then you can think about reconstructing distribution of physical parameters. So this is kind of key ideas. And when we are speaking about the expansions, we are speaking about the outer and inner expansions. There is a small parameter, I will show you examples. There is small parameters in the equations, and then we can make two kinds of expansions. Either we are far from the inclusion we want to image, or we are near to the inclusion. And the expansions are completely different, and the information contained in these expansions are completely different. That's why from inner or internal measurements, there is a hope to make distribution, reconstruction of distribution of physical parameters. We can reconstruct functions, but from far measurements, there is filtering effect in these equations, and then many information, a lot of information is lost, and there is no way to reconstruct it back. Okay, and this will be clear in this outer expansions. Okay, now what's the plan of this talk? So I will start with a very academic problem, this conductivity problem. And we'll show you outer expansions, how they look like, inner expansions, and then I will show you this super resolved imaging. There is a way to make super resolved imaging, but you need very good signal to noise ratio. You need very good data. Anyway, then I will show you frequency domain imaging. The idea is to compare different imaging functions. Then I will move to time domain imaging. So my main interest would be to try to explain this time reversal methods. They are very natural methods, and to show how to correct two important effects in imaging: attenuation. There is attenuation, acoustic and attenuation when we deal with ultrasound or with photoacoustics, and then when there is a random fluctuation in wave speed. And then I will show you how to apply this expansion method to derive multiphysics imaging approaches. And then I will conclude with a few remarks, mainly on elasticity. Okay, so just to write equations, let this omega is my background domain, and my inclusion is D. It has a different conductivity. The conductivity it's not written here. And the next equation, the conductivity in D is some parameter k different from 1, and the conductivity of the background is 1. And I would need two things, two functions: the Newman function, which is n, which is the Newman function of the Laplace equation in the domain omega, and I would need this function v. It's a function defined in the whole space. So scale this to b, and then define the function is harmonic outside, it is harmonic inside, and with the jump conditions on the boundary. K is the parameter, the conductivity parameter inside, and it behaves like x at infinity. Actually, if you are familiar with homogenization, this is a homogenization character. And now this is the equation I wrote in omega. So U is the potential, and its solution to the conductivity equation, where there is an inclusion D that I want to image. And I will denote by capital U the background solution, which is just a harmonic function inside the domain. Okay, now when the inclusion is small, it behaves like a dipole, but it's polarized dipole. And this polarization is through the matrix M. I don't have a pointer, but anyway, it's through the polarization. Through there is a in the corner. I thought this one. Oh, yeah, I like it better. Okay, so this is M. So when the inclusion is small, it behaves like a dipole, but polarized, and it's polarized through this matrix M. I will call it polarization tensor. And this M is constructed, it's given by this formula, and it's constructed using through V. V is the homogenization character. And if you look at it, it's mixture of parameter information and geometry. Indeed, it's a low frequency. It contains only low frequency information because it's an integral on B of some function defined with B. But we integrate, actually, I will show you, we integrate oscillation. All the oscillation in B are lost. Okay. So, and there is a canonical correspondence between everybody looks like ellipse. So the only thing that you can reconstruct from here, if the inclusion is small, and your data is almost given by this approximation, so your signal to noise ratio is not too high, is the location of the inclusion and its equivalent ellipse. This is the only information, and there have been a lot of algorithms and a lot of work by many people on this. Okay, so because M plays this polarization plays an intriguing role, we have to understand all the information contained in M. And actually, it's a 2 by 2 matrix in dimension 2, but it contains a lot of information, and it tells actually a lot of things about the inclusion. So it's a symmetric matrix. It's positive if the contrast inside is higher than if the contrast is higher than 1, k is higher than 1. It's negative if k is smaller than 1, and the trace of M and trace of M minus 1 satisfy this bounds. Actually, these bounds are optimal in the sense that any matrix satisfying this is the polarization tensor of some domain at fixed volume and fixed conductivity. Okay, now let me show you this what the polarization looks like for two inclusions. Assume that you have two inclusions here, the polarization tensor, and they are next to each other. This distance is a further the size of the inclusion. So you have a clutter, and the polarization tensor of these two inclusions is the same as this one. So the only thing that you can reconstruct from boundary measurements is this inclusion, not these two. And the reason is because in reconstructing this, you need high frequencies. It's a very high frequency information, and you don't have it in the data. Your data is just like this. The high frequency information is lost by integration, and then the only thing that you reconstruct is a low frequency approximation of these two. Okay. Now, if this one is more conducting than this one, then it moves the equivalent. The equivalent inclusion moves to the one with the highest conductivity. And if it's much larger than the one next to it here, the equivalent one is almost the one for the largest. Okay, so what to do? Using this, the only tells you that if you don't have very high signal to noise ratio, then there is no hope of super resolution. Super resolution is to be able to image a clutter like this, two inclusions like this, and get them separately, not get the equivalent inclusion. Okay, and the other thing is, if you look at this M, it's a mixture of K and geometric information, and there is no hope to separate the geometry from the parameter. So you make the inclusion smaller and with higher conductivity. It's the same as a larger inclusion with lowest conductivity. So if the signal to noise ratio is not enough, thanks a lot. What is this is not enough, you will never be able to separate the conductivity, the material parameter, from the geometry of the inclusion. So we want to make super resolved imaging, and we want to get the conductivity. And you need to pay some price. So the price is a high signal to noise ratio. So you pay this price, and you have this asymptotic expansion. It means what? It means like your inclusion, which is very nature. It's a dipole plus quadrupole plus a higher order dipoles. So that's all. And these ones we have a formula for these ones, and actually proof of this asymptotic expansion. So I will call this M, alpha, beta. I will call them higher order polarization tensor or generalized polarization tensor. And actually complete asymptotic expansion is possible. And actually I stopped here up to the volume to the power 2, because after you have interaction between the inclusion and the boundary. But it's possible to write down complete asymptotic expansion. Okay, now delta is the characteristic size of D. Actually, D is like a D plus delta some domain B. It has not to be a ball, so whatever it is, but it's characteristic size, and the characteristic size of B is 1. Okay. Now, what is good news is that this higher order polarization tensor can be obtained from boundary measurements. Okay. So what to do with higher order polarization tensor? They have actually a lot of properties. They are symmetric, but on harmonic polynomials. They are positive on harmonic polynomials, and actually they uniquely determine the inclusion and the material parameter. If you know all of these polarization tensors or combination of harmonic so you know all of these polarization tensors, then you know exactly the domain and you know exactly the conductivity. But in practice, you will never get all of them. You will stop at some order. You will get the 3, 4, 5, 6. So the idea is from 5 or 6 polarization tensors, what kind of reconstruction can get? Can we get the super resolved reconstruction? Okay, so I didn't write down the definition of the polarization tensors, but I can write it. There are many ways. So M I defined it throughout V, that's harmonic function, and we can define M alpha beta throughout similar V alpha. So it's something like the gradient of this V alpha times the gradient of X beta, something like this. And where V alpha behaves like it has to be harmonic polynomials at infinity of order alpha. And actually, there is better representation of this. If we let me write it down, because this operator is a great operator. So if you are familiar with integral equations, K star is either the called trace operator or a Newman Poincaré operator, and it's given by integration on the dB x minus y is nu of y. This is the normal derivative at y, x minus y 2, and if you apply it on phi, this is phi dy. And the polarization tensor M alpha beta, let me write down the formula. It's nothing else than minus K star minus 1 of X alpha dx beta d normal derivative of X beta, and you apply the inverse of the operator lambda identity minus K star on X alpha, and lambda, to relate lambda with K, it's K minus 1 to K plus 1. So I like much better this definition than the one with the functions V. So M, the first order polarization tensor, corresponds to alpha equal 1 and beta equal 1, and it's defined through this function V. And the other ones, you put here polynomial sum of A alpha xi to the power alpha, when this is a harmonic polynomial, and you put here and that's all. Or you put here the normal derivative of this xi alpha, and then you integrate this against x beta. Okay, so it's they are not strange quantities. They are very nice quantities because they tell a lot of things. And now, okay, you can get estimates of harmonic moments of the domain from this generalized polarization tensors. And it looks we have also Wiener type bounds, and we have you have a lot of properties in this book, this polarization tensors. And our thinking is to make representations of shapes through this polarization tensors, because actually they uniquely determine the shape. This is theorem, and then it's reasonable to use them as a representation of shapes. Okay. Now, how to get super resolved? So imaging, we get this M alpha beta, this polarization tensor here, and then we want to make minimization. This is the only thing that we can make. So we make an optimal control algorithm. We minimize the discrepancy between what is measured. This is what we measured, and between what is computed, and then hope that we will get the domain. So we have a domain, we measured its polarization tensors, higher order polarization tensors. We want to get the domain back. We compute the polarization tensors for given domain and minimize the discrepancy function. And actually, we tried this and it didn't work. And the reason is this higher order polarization tensor. So let me put this is. And this is alpha and beta. So the important thing is alpha plus beta. What is the sum of alpha plus beta? Actually, for k equal 1, this is or k equal 2 starts with k equal 2. Everything is like ellipse. For k equal 3, it starts to contain better and higher order information on the domain. For k equal 4, it's getting better and better, and getting higher and higher information. So when you minimize until k equals 7, you minimize the whole thing. Your algorithm will make a compromise between high frequency component and low frequency component, and we will never get you to the high frequency component. because this is life. So this algorithm will make a compromise on everything. Now the idea to get this high order information or high frequency information, because it's kind of unstable. So when you make optimization on everything, the stability is natural. So it will go. You will lose the resolution. This is resolution, and always the resolution goes with instability. You want better resolution, you have to pay some instability. So the way to do it is make optimization on this two, get initial guess, get something, use it like initial guess, and either you can make optimization on this, including higher order information, or you can make optimization on the other ones using this initial guess. And it looks like a better idea is the first one. Make optimization on the first one, two first, then get the result, use it like initial guess, and include one more information, and then continue. And this is like a hoping algorithm, and it works well. We have a clutter here. Initial guess is using the first order polarization tensor equivalent ellipse, and after 6 iteration means that you are using alpha plus beta equal 6. You are using 6 family of polarization tensor up to order 6. This is the reconstruction. Here, this is the reconstruction. Here, this is the reconstruction. As you see, this is a good reconstruction actually, but it couldn't change topology. And the reason is if it's not included in your algorithm, the algorithm will never make it. So we have to include the level set formulation of the algorithm. And if you include level set formulation of the algorithm, then your optimal control algorithm can change topology. And this is the reconstruction using level set formulation. So there are 3 inclusions. This is no without no's. This is with 1% and 5%. It gets the 3 inclusion from 6 polarization tensor. So actually we have 2 statements or something like that. Not conjecture, but statements. First one is so I forget the first one. Let me tell you the second one. The second one is this polarization tensor tells you the topology of the object, but we do. So let me say it again. You have some clutter. So clutter means a clutter of simply connected domains. Okay. Now you compute their polarization tensors. How many you need to say that I have here 5 simply connected objects? It looks like it's at 2 times. So you need k equal 2 times the number of. It's not theorems. It's just we are making computations. So 2 times the number of the inclusions simply connected. So it looks like that this polarization tensor is first statement. Now I get it. Is a good thing for representing domains, for representing shapes. It's very natural in imaging because this is the quantity it come out from the asymptotics. So we have to deal with domains using the polarization tensor and forget parameterization of domains. This is the right parameterization of the domains. And the other thing is about this topology. So call it whatever, the number of simply connected components in the clutter. I think that you can get it from the polarization tensors, making numerically using this level set formulation, but analytically it would be great actually. It tells a lot on the topology. So we got very excited about this. Okay, let me now this is outer expansion and get super resolved imaging. Now if you use the inner expansion is different. Inner expansion, there is no integral on B of the corrector. The corrector itself comes out, and then this is the inclusion, and this is your inner expansion is here, and this is a lot of information. And actually, you can make algorithms which are boundary independent. You can make boundary independent reconstruction. When you have measurements here, you don't need to compute the boundary here, or to know exactly the boundary, to make to reconstruct the inclusion D, which is great because all of this boundary, all of this imaging system based on boundary measurements, they are very sensitive to the boundary. So if you have inner expansion, you have boundary independent reconstruction. No need of exact knowledge of the boundary of the domain. And you have local reconstruction. You don't need to know the domain, to have the data everywhere. You want to image this part, have the data here, and you can get good approximation of geometry and separate the conductivity material parameter from the inclusion. There is something that I would like to point out, which is there is a trade-off of resolution and stability. So assume that you have measurements everywhere. So this is assume you have measurements everywhere. So you can choose what kind of measurements. So let me show it here. Your inclusion is here, and you have measurements everywhere. So what's better, to use all the measurements or use the measurements on smaller domain, or what is the best? What is the size of the domain you will include on your optimization? If you use the whole domain, you will get good stability but better resolution. If you use a smaller information, you will get better resolution, but it becomes unstable. Okay, actually I know we know what is the optimal size for this, but we know it for wave propagation problem. It's almost of the same size of the wavelength. But for conductivity, actually we have ideas. It's harder to figure out what is, because there is no wavelength in conductivity problems. So this is reconstruction. This is the field here, inner expansion, and this is the reconstruction. So maybe you're not familiar with this, but this is my old lab. This is Center of Mathematics Appliquée of Ecole Polytechnique. So, and actually I didn't change this because my new lab is a DMA. It looks like it's easier to reconstruct. There are 3 letters, and this one is much higher, much. So, and actually the parameters inside are correct. So this has been done by Pierre Garapon, who is now in Stanford. Okay, and this is what I was talking about here. What measurements you should include in your algorithm? You include the whole measurements. If you include this is the target. If you include the whole measurements, you get better resolution, because it's exactly the same idea as here. Your algorithm will make optimization will make compromise between high frequency information around the inclusion and low frequency information far away from the inclusion, and then it will choose kind of not very well resolved image. If you choose only this measurements, then you can get a much better reconstruction, because you make optimization only on the high frequency component of the signal. Okay, now let me move quickly to the frequency domain imaging. So frequency domain is you have waves, and we want to make reconstruction algorithms or shape representation wave imaging, and the central idea is you have to kind of to make the best imaging algorithms, you have to understand the physics. And if you look at all of these algorithms, because the problem is depending on the wavelength, on the signal to noise ratio, and the distance to the target, you have to make it very specific. So if you are in the far field measurements, there are specific algorithms for far field measurements, and they will not be good idea to use if you are in the near field measurements. The information is not the same. So your algorithm has to be very specific to this. Okay, so let me just show a reconstruction of small inclusions in the far field measurements, and if you are not familiar with what is the signal to noise ratio of there is no n here, of an imaging function, it's just the expectation of the imaging function for a fixed frequency at the location of the inclusion over its square root of the variance. Okay, so for conductivity for wave imaging, let me consider this. Sorry, make it very brief because it's. Let me consider this setup. Actually, it's a kind of practical setup. This is the inclusion. Now it's in the free space, and either I have an array of transmitter, so and the receiver. Let me take it the same, like this, or it's an inclusion and array of a transmitter and receiver surrounding the inclusion. What is an array of transmitter and receiver? You send a wave here. It will be reflected by the inclusion, and then you collect the signal here. And from this, and then you change the position of sending the wave, and you collect the information on the other, right? And then what you get at the end, you get a matrix called multistatic response matrix. So here you excite this point, you send the green function, and then you collect the signal on your array. Okay. So this matrix actually it's a complex symmetric, but it's in the absence of noise, but it's not a Hermitian matrix. And what we want to reconstruct the target D and to reconstruct its electromagnetic parameters or acoustic parameters from this matrix. Okay, so if you have a matrix, the only thing that you can do is singular value decomposition. But where analysis is there is to understand what is in the signal value decomposition of this matrix in terms of what? In terms of the location, the geometry, and the parameters. And if you understand this, you are done. Then you can write down a good optimal or good reconstruction algorithm. So this is the expansion. This is the effect of a small inclusion like this on the measurement. So what you measure is what is just derivatives of the green function. So this point is z, this point is x, this point is y. So what you measure is the green function between x and z times some functions, which is called, this is polarization. It's not. They are functions of the domain and the electromagnetic parameter. This is polarization tensors, but times the green function or derivative of the green function between this point and this point. That's all. This is the asymptotic expansion, and this frequency dependent. This polarization tensor now are frequency dependent, and if you take their limit, when delta goes to 0, they will give you the polarization tensors I just show, right? Okay. Now this is the structure of your matrix. It's derivative of green functions times some matrix W, which contains all the geometric and material parameter information, times the green function. From this, you want to design to locate Z and to reconstruct the electromagnetic parameters and some geometry, some approximation of the geometry. So there are many algorithms to do this. So let me show you the structure of the singular value decomposition. Here there are two inclusions, and both are magnetic and electric inclusions. So you have 6 singular values, and you have 6 because each inclusion, the signature of its inclusion is 3 singular values, 2 for the magnetic part and 1 for the electric part. Okay, if this inclusion is small compared to the wavelength, if it's large compared to the wavelength, look at the structure. It's much complicated, much more complicated. Almost, this is 1 inclusion. So for one inclusion you have 3. If it's smaller than the wavelength, and if it's larger than the wavelength, you have for 20 by 20 matrix, you have almost the half matrix. There are 10 singular values significant. They contain information, and it's very hard to say which eigenvalue is associated to which information, which quantity. So when you have this situation, direct imaging can be designed. You can make direct imaging. When you have this situation, the only thing that you can do, at least the only thing that you have been successful for, is optimal control approach. And now we identify, we have good ideas on who is he, who is who. Okay, now you want to make reconstruction algorithms. So there are many reconstruction algorithms actually. There's backpropagation, migration, music type, topological derivative based imaging function. There are many of them. But actually, let me give you just one key idea. Let's look at this backpropagation. Many of them are subspace weighted projection algorithms. So you project something, always you project green functions on the significant singular vectors. This is the idea. And then there is it depends on your weight, or it depends on how you are making this. You can make nonlinear functions, whatever you to get the inclusion. But actually, the main idea is this: if you project the green function and its derivative, you will never get super resolved imaging for waves. Why? Because this is the green function and its derivative. It's just source plus dipole approximation of the inclusion. So the resolution we'll get from this is really a resolution, and you can forget it. Now, what you can do to have super resolved imaging, so you have all of this in the data. You have many of these derivatives. So if you project 0 derivative plus 1 derivative, you will never get a high resolution. To get high resolution, you have to project a higher order derivatives of the green function. But then it's kind of unstable. So always there is trade-off between resolution and stability. If you project higher order derivatives of the green function, you can get the super resolved imaging. If you project 0 derivative plus 1 derivative, you can forget it. It's impossible. Okay, so the just figures. This is what the backpropagation look like. This is what music look like. It's sharper, but it's not more resolved. And now actually there is a very natural idea. Assume that you have measurements over many frequencies. Can you make the algorithm better? Actually, what we notice it is there are two cases. Either there is correlation between measurements, or the measurements are uncorrelated. So if the measurements are uncorrelated, you can increase the signal to noise ratio just by effective increasing, because you have many measurements, and that's all. If there is correlation between measurements, is because of medium noise, you will have correlation between measurements, and then it's unclear whether multi-frequency measurement makes better than single frequency measurements. And the idea is better idea is to use this coherent interferometer. Let's call it SINT. Done mainly by these people. I will show you what we have been doing in this SINT. So this is comparison between the algorithms, and actually the best one. You have two things. If you want to compare imaging function, compare them with respect to measurement noises, but with respect to medium noises too, because it depends. If you have medium noise, you have to compare them and the best one for medium noises could be the same, but could be different for the best one with measurement noise. So looks like I think that we proved it. The best one for medium measurement noises is backpropagation. You cannot do better than backpropagation, so just backpropagate. So the one I showed you, and this is simulation of realization of medium noise, and the best one for medium noises, it's unclear. So we have this for single frequency. We think that the topological derivative gives the best result. Anyway, okay, now so now what we can do with waves, it's the same. So in the time domain, this is a frequency domain. You have frequencies, and your frequency is fixed, or you have. Now, if you send wave in the time domain, so you send it like this. What can be done? And actually, it's very natural. If you create this green function for the wave equation, it contains all the frequencies. So since it contains all the frequencies, there is no hope to make expansion. The inclusion is small with respect to what? So you have to truncate your signal, and once you truncate your signal, it's done. You can prove some expansion. So truncation of the signal is you truncate. This is the inclusion is of size, let's say delta. So take all the frequencies smaller than 1 over delta. If you take all the frequencies smaller than 1 over delta for any of these frequencies, if you take the frequencies smaller than 1 over delta and you truncate the other frequencies, then you can prove this asymptotic expansion. And it's natural one. So the inclusion is here. You create the green function. Nothing is happening in the medium. It hits the inclusion, and then there is a polarized wave created by the inclusion, and that's all. And this polarized wave is polarized with respect to m, and it's just. But you have to truncate the signal, otherwise it doesn't make sense. And you truncate the high frequencies here. So once you truncate this, the high frequencies here, you truncate the high frequencies of the signal, the measurements, and the high frequencies of the measurements are in terms of the truncation, which is kind of miracle. It's the truncation of the source times the polarization tensor. It's polarized, and then it's a wave, but without high frequencies. That's all. Okay, so you can use it, and to make time reversal. So once you get this, you say you are here or whatever, or from limited view, whatever, and then you measure the signal and you send it back, and it will focalize on the inclusion, and you are done. But in practice, there's two problems. The first problem is the attenuation in the medium, and the second problem is your medium is your wave speed here is not homogeneous. It could be variable, but at least for acoustics, variation is very small, and then you can make asymptotics with respect to the attenuation and with respect to this fluctuation of the speed of the wave to make a time reversal. So this is what we have been doing recently. So let me show you results. So the idea is 2 minutes. Okay. So the idea when you have this is the idea. When you have attenuated attenuation, so attenuation is let me think about attenuation is don't know what I have equations here. Attenuation is let me think about it like a quadratic attenuation. So it's do I have equation? This model. This is thermoviscous model. It's simplest but most used model. And when you have attenuation, what you do is the following: get your signal here, the data, call it GA. If you time reverse this because of the attenuation, attenuation is in this direction. It's exponential decay of the energy. In this direction, if you send it back, it's exponential increase of the energy. So if you have noise here and you send it back, you will lose everything. So you have to pre-process the data, and you pre-process the data with some operator constructed through stationary phase theorem. And once you pre-process the data, you use the classical time reversal, and you will get a good image of this point, which is like a source. So this is the example. So this is the reconstruction by the sources here. No. and the measurements are here, and then we pre-process the measurements here, and with higher order filter, and then we get a kind of a very good reconstruction. If you do it with time reversal without this pre-processing, you don't get such an information. Now, if you have cluttered sound speed, then the idea is simple actually. How to get rid of this clutter speed? The idea is simple. You have measurements here, G, and you have because of its wave equation. You have all the frequencies. You have multi-frequency measurements. The idea is because of this clutter speed, the phase is very much perturbed. Now, what you do is to back propagate the coherent information. So take two frequencies, G1 and G2, and take omega 1 close to omega 2, and take these two data on x1 and x2 close on the surface here for two close frequencies. Then the main problem is coming from your phase. What you do is just multiply this one by the conjugate of the other. Then the phase will cancel out, and then you back propagate in constant medium. And if you back propagate in constant medium, you get good results. I just want to go for 1 minute. Okay, you will get so this is the random velocity, and this is reconstruction with Kirchhoff without this Sint algorithm, this truncation of all the incoherent information, and this is the reconstruction with the Sint. Okay, this is another reconstruction for point sources, but now the random medium contains high frequencies, because actually the frequency of the source has to be comparable to the correlation length in your random medium. Otherwise, there is no need to make such elaborated things. Okay, one word on multiphysics. I'm done. So multiphysics is this is a quite hot topic, and actually I think that this is the first book where some of these methods were explained, and some mathematics have been done. And how this multi-frequency, how this expansion methods are used there. Take the conductivity problem. This is what Guillaume didn't explain this morning. Take the conductivity problem and make local changes. So heat a little bit, then the conductivity will change a little bit, and measure the perturbation due to this local change here. And then using expansion methods, you can write asymptotics for the perturbation. And what you get at the end of the day is the electric energy, gamma gradient 2 square, from this perturbation. When you scan, you scan your domain. You can do it also for Helmholtz equation. So then you have the choice. Either you substitute gamma by the electric energy over gradient 2, and you end up with this zero Laplacian, and then there is from here you have to solve it, but there is no way to solve it other than iterative way. Or you get this information, E equal to gamma gradient 2, and you make optimal control algorithms. And our experience shows that it's better to make optimal control algorithms than make this iterative resolution of the zero Laplacian. You can do it for Helmholtz equation, and you work a little bit more, and you get both. You get the electric energy associated to the conductivity, but this you have a kind of the Q times U square. And then the same, you have either you substitute and you get a nonlinear PDE, modified zero Laplacian, or or you make optimal control. And again, optimal control is better. And the reason is that because it's more efficient approach within complete internal data. If you have to solve the zero Laplacian, you have to get the data everywhere. Then I'm done, for sure.
Okay, thank you.
No, there is a conclusion. Just one slide. I'm done with it.
5 minutes more than.
I'm sorry. So when you have, but I'm sure Adrian is interested in this. Okay, I can get one more minute. Okay. Okay. So I conclude. I'm sorry for this extra 5 minutes, but it looks like these expansion methods are powerful strategy for increasing stability and resolution, and they combine a variety of math and computation tools. They can be extended to elasticity. There is a very nice book edited by Otmar, and there is a chapter on this in that book. And it looks like this story has still a long way to go. So that's why I'm going back and have to work a little bit more. So, thanks.
I think in view of the tour and the extended lecture, perhaps you could leave any discussions with the speaker for private conversation after. Thank you. That's the afternoon.